In the last video we explained that a rotational body remains at its speed of rotation with its inertial torque. This persistent force arose because every point mass in the body has an inertial force that opposes the force acting in the tangential direction, which forces the body to change its speed. We have explained in the video extension of the centrifugal force that this point mass also opposes the force that acts perpendicular to the plane of rotation, and with the same strength. Assume that a force F acts perpendicular to the point P. In relation to the center of the disk, the acting force corresponds to a torque that forces the plane of rotation to tilt. Against this, the point mass reacts to remain in its state an inertial torque. So the body remains with this inertial torque of the point mass in its axis direction. If a torque m equals Fl, whose point of support is equal to the center O of the body, acts on the axis of the body in order to change its direction, then each point mass is opposed to inertial torque in relation to a z-axis that is perpendicular to m and runs through point O. This equation shows us that the inertia torque of a body in relation to any point is always equal to the square of the speed, regardless of the direction of movement. To analyze in detail, let's enlarge this sketch. The torque mz forces point P to revolve around the z-axis. Against this, the point mass reacts with an inertial torque m. Because this inertia torque of each point is different in relation to the z-axis, the sum of the inertia torque for bodies must be calculated as follows. By solving this equation we get the inertial torque with which the body remains in its axial direction. So the inertial torque with which a rotating body of revolution remains in its axial direction is the same as that with which it insists on its speed of rotation. It is not surprising that a body remains in its various states with the same mechanism. It is interesting that the inertial torque is independent of the distance h to the related point. If we move the contact point of the applied torque from O to O*, if the body is forced to revolve around the z** axis, the inertial torque, which opposes the imperative, remains unchanged. This means that the point of application of the applied torque on the axis of rotation, x-axis, can be freely selected. This can change the strength of the attacker, but not that of the body's inertial torque. So with inertial torque, a rotating body remains in its axial direction. To tilt the axis, a torque is required that must be greater than the inertial torque. And the condition to maintain this acrobatic position of the gyroscope is that the inertial torque must not be smaller than the torque ma caused by Earth's gravity. The gyroscope has an even more mysterious behavior. If we try to tilt the axis direction of a gyroscope with a torque m which is smaller than its inertial torque, the axis will be tilted in a different direction instead of the one to be expected. As shown in the figure, if you try to turn it counterclockwise around the z-axis, for example, instead of turning in this direction around the z-axis, which should actually have happened, the body reacts by overturning the x-axis up. This effect illustrates a phenomenon: when a force encounters an insurmountable resistance, its direction will overturn. This phenomenon looks quite mysterious, but can be explained with a simple example. If the water cannot flow downwards in a container, the direction of force directed there is tilted 90 degrees to the left, where there is a way out to let the water out through a hole on the sides. So the direction of pressure coming from above has flipped to the left. And just as the water pressure has not changed with it, the force after overturning with the gyroscope remains unchanged, because this overturning was not hindered by frictional resistance and the like. We take note of the fact that the direction of a force can change if it hits a resistance. We will find out later how this phenomenon occurs in nature. But why is the x-axis tilted up and not down? To answer this question, we will transfer this example of the disc-shaped gyroscope analogously to a spherical gyroscope. Because the torque m causes a rotation omega2 around the z-axis. Then the two rotations omega1 and omega2 are superimposed on a third rotation omega3. If the body can only rotate around the x-axis, which is the case with a conventional gyroscope, the x-axis is inevitably tilted in the direction of the z-axis. The direction of tilt of the axis of a gyroscope can be determined by holding a ballpoint pen as the axis between your curved fingers and stretching your thumb upwards. The ballpoint pen shows the direction of the torque. If you try to turn the axis in the direction shown by the curved fingers, it will tip up in the direction shown by the thumb. If a gyroscope is in such a position as shown in the figure on the right, the torque ma generated by gravity, which forces the gyroscope downwards, is compensated by the inertia torque. In this situation it can be observed that the whole body now circles around point A. This is the so-called precession movement. The reason is that at this position of the external torque it is not possible to tilt the x-axis downwards. As a result, the direction of the applied force F is lowered horizontally in accordance with the rule of force overturning. Then the force F drives the body horizontally counterclockwise to revolve around point A. Now we ask a question: how fast should this speed be? According to previous physical knowledge, the speed of an accelerated body will continue to increase over time. That is obviously not true here, because we cannot observe an increasing speed of this precession movement. So it can only be calculated with the equation of inertia. Because the body circles around the point O*, the radius of circle must be h. Then you could think that the speed has to be like this. But that's not true. This is the same as we explained in the video extension of the centrifugal force, why the centrifugal acceleration az is wrong for the conical pendulum. As I said, the radius for inertial force is not always the same as that of the circle on which the body moves, but always the same as the distance to the related force. Because the body falls from point A, the length L is the radius for inertial force. Then actual speed is as follows. And the torque that drives the body is the same as follows. This is equal to the torque that forces the body to turn downwards. This in turn means that the strength of the attacking force remains unchanged after overturning. So the speed of the precession movement depends, among other things, also on the position of the gyroscope or on the angle theta. When theta is 90 degrees, it is 0. Thank you very much for your attention. See you next time.